Hi, this is Kevin Trainer, and welcome to part one of my lecture on chapter 7 of the third edition of the Zelle Python book. Chapter 7 is about decision structures. And this is really the first time within my course we're going to deviate from covering the material in the chapter from beginning to end. This chapter is very well written for the math inclined. Okay, so the main example program has to do with solving quadratic equations. And if that excites you, then this is going to be a great chapter for you. Unfortunately, most new programmers are not so excited about quadratic equations, and they get turned off. So, in terms of reading the chapter, please do your best to pick the things out of the chapter that are not so math heavy. Okay. I am going to go through a set of supplemental sample programs that I created several years ago for this chapter when it was in the second edition, and I've revised those and added to those, and so most of the explaining that I'm going to do is going to be around my own examples. And in fact, I'm going to be offering them in this chapter as an alternative to separate tutorials. So here's what I'm going to be using over the course of the lecture. I'm going to be using the slides that came with the book, which you see here. I'm going to be using a project which you should be able to download out of your other resources section of your weekly schedule. It's called Demonstrations to Supplement Zelle 3E Chapter 07. And you should be able to download it, unzip it, and it has a series of examples that where the program names are numbered in sequence to help them show up in the order that I'd like to talk about them. Okay, and they start with simple decisions or selections, and they go all the way down to how to create a module that houses utility functions and call the functions from another module. Okay, which are all things that are covered in the formal chapter 7, but I like my examples better. Okay, so we'll be going back and forth between these. All right. Okay, let's get started. I'll leave you to read the objectives. So far, the programs that we've done so far are simple sequences of instructions where one followed the other. Now, there have been a couple of exceptions to that. One is that we learned how to do loops. Okay, and a loop has a block of code, and the block of code is the body of the loop, and we do execute the body in sequence, but we do it repetitively. Okay, that was a peek ahead. All right. The other thing that we've done is that we've learned is within a sequence of instructions, one of those instructions can call a function, and that function will be executed in sequence, and then control will come back and will execute the next statement in the sequence of the calling program. Okay, and in the last chapter, chapter 6, we did quite a bit of that. We generally consider calling functions just kind of a special case of sequence. Okay. So, in fact, we'll talk about that further in a couple of minutes. Okay. Now, using sequence and to some extent even repetition in loops doesn't get you everything that you need to do in order to solve a typical problem. Okay. Typically, we need to make decisions. Okay. We need to make some kind of choice. We need to select between two or more alternatives. We might have optional behavior. So what we need is some structures to help us to do that. Okay, and that's what we're going to learn about here in Chapter 7. So these structures that help us to control the logical flow of the program are called control structures. Okay, they help us to alter the sequential flow of the program. The ones that we're going to learn in this chapter have to do with what in this text we call decisions. Okay, and in some computer science discussion, we call this selection. Okay, when we make a decision, we select between alternate bits of code that we're going to execute. So you can see how decision and selection are really two names for the same thing. So in this chapter, we'll learn about decision structures, which are statements that allow a program to execute different sequences of instructions for different cases, allowing a program to choose an appropriate course of action. Cool. So the first example that we have in the Zelle book is this convert.py, and I'm going to discuss that in a minute. But before I do this, I want to have a little bit more of a general discussion about a Wikipedia article I gave you a link to in your weekly schedule. And that's a Wikipedia main article called Structured Programming. Now, what's kind of funny is when I got into programming, which was, 40-some years ago, not all programming that people did was what we now call structured programming. People wrote programs in pretty creative and wild ways. One kind of interesting thing that they did is that there was a very popular statement called go to, in which you could send control of the program to another place in the program, and it would go there and it would never come back. And there were all kinds of creative ways to use the go to, and there were a lot of people that really thought it was a great thing to do. So this kind of jumping into things and jumping out of things was a common approach that programmers had early in. Well, along came these people who came up with this thing called the structured programming theorem, which is, let's see, the research on this was done in the mid-1960s. So about the time I was getting into programming in the 1970s, people were really starting to take this pretty seriously. And so when I learned to program, at least in industry, we were taught to only do structured programming. So what are the elements of structured programming? Well, they're down here under control structures. So we have the sequence. We've already learned how to do that. Okay. That's as it describes here in the Wikipedia article. This is ordered statements or subroutines, read for our language, functions executed in sequence. Well, we know how to do sequence, okay? Then they said, well, another control structure that was good and you should use it was selection. Those are the decisions we're going to be learning about today. The third control structure was called iteration. Okay, that's looping. Well, we've already learned a little bit about looping, but we're going to learn a lot more when we get, I think, to the next chapter. Okay, and in this article, they say that there's another control structure called recursion. This is a really unique approach to computing where a function will actually call itself, which one would think might go on forever, but there's a creative way to make sure it doesn't go on forever, and it's a really elegant way to solve a lot of problems. In the Zelle book, that's the subject of the last of the chapters. It's not one that we cover in our course, but it is the thing that might interest you and you might want to read on your own either now or after the course. So when I learned about structured programming, we didn't even say that recursion was included, and so we said there were three things that you could do: sequence, selection, iteration. And in the languages that we were using in the early days, that meant we couldn't use all the features of the languages. Well, that's not true anymore. So it turns out that modern programming languages are structured by design. So a programming language like Python is very hard to write unstructured programs in, okay? Primarily because they don't have the goto statement, but also because they don't have some other features that created some logic that was not one of sequence, selection, iteration, okay? So it's been pretty well accepted for over 40 years that good programs are structured programs. And because of that, modern textbooks and courses don't really make a big deal of it. Okay? And so structured programming is just programming. Now. Why? Because we don't give you the tools to create unstructured programs. You can do some, I mean, if you try hard enough, you can do some unstructured things. But for the most part, if you use the tools that we give you and you use them in the way that we teach you to use them, you're going to wind up with a structured program. And the selling point for structured programming was it was easier to design. It was easier to code, it was easier to test, and it was easier to maintain. And it was less likely to hide undiscovered defects or bugs. Okay? The only two drawbacks that structured programming had is the people who used to jump all around the place, well, they thought it was boring. Because when they were jumping off to exciting places, there's always a sense of kind of excitement and wonder. Well, that wasn't a good criticism. The other thing that people were worried about in the early days is, perhaps with all these kind of functions or subroutines that called each other, that there'd be a lot of overhead and it would be kind of slow. Well, computers are a good 10,000 to 100,000 times as fast as they were 40 years ago. And because of that, nobody worries about that anymore. Okay, so structured programming is programming, and we're learning about the elements of structured programming, the control structures. We've already learned about the sequence. Now we're going to learn about the selection. And then we're going to learn more about iteration, which we've had a peek into in the early chapters. And again, recursion is kind of serious. It's a serious computing approach that is interesting, but I can tell you this: I worked for years and years in industry without ever using recursion. Okay, which is one of the reasons that I don't include the recursion chapter in the course. It's just a potential confuser. Okay, so enough of that. So that's structured programming. These are the control structures that are part of it. The second one, selection, that's what we're calling decision in chapter 7. Okay, and they're just alternate names for the same thing. All right? Good. Okay, so let's look at this convert. Okay, so this is a program that prompts the user for a temperature in Celsius, and it converts it to Fahrenheit. So you can see that we do an input. We convert it to float with float. Okay, we put the answer in Celsius. Then we convert it by doing 9/5 times Celsius plus 32. Again, I would have put parentheses around 9/5 times Celsius. And then we print the answer. The temperature is Fahrenheit degrees Fahrenheit. Okay, so that's pretty straightforward, right? And there are no decisions in here yet, right? So let's go ahead. So let's say we want to modify the program to print a warning where the weather is extreme. And this is a classic way that we teach these decisions. And in fact, the examples that I put together in the companion supplementary project are all based on the weather and what we say about the weather. So this is kind of a tradition, not quite as strong as Hello World, but close to it. So here's what we're going to do. We're going to get the temperature, and then any temperature over 90 degrees Fahrenheit and lower than 30 degrees Fahrenheit will cause a hot and cold weather warning respectively. So if it's 90 or greater, we'll warn about hot weather. If it's 30 or less, we'll warn about cold weather. Okay? Okay, so on this slide, he has kind of the pseudocode, okay? Except that he gets one of the decision signs wrong, okay? So again, he prompts for the input, he converts it, then when he goes to output it, he says if Fahrenheit is greater than 90, print a heat warning. If Fahrenheit is, he meant to say less than 30, print a cold warning. And then one problem that I have is that it's very hard to tell that a program has run if you don't produce some kind of output. So in terms of the design, I think this is kind of weak in that there's a whole range of temperatures for which it's just going to be silent. So everything starting at 31 and ending at 89, it's just going to look, is the program actually running? Is it done? It's hard to tell. Okay, so maybe that's not the best design. But let's look at the code. So this algorithm has two decisions at the end. The indentation indicates that a step should be performed only if the condition listed in the previous line is true. And that's how these decision structures work in Python. Okay, so now what are we looking at here? Well, we're looking at a programming flowchart again, programming flowcharts as a way of explaining programming logic, they've been around for, well, a good 60 years, okay? And why don't we use them so much anymore? Oddly enough, one of the reasons we use them as much as we used to is has to do with structured programming, okay? You can actually diagram things using these programming flowchart symbols that break the rules of structured programming, which is to say that they have a control structure other than sequence selection or repetition or iteration. Okay? Well, every once in a while, so that's why we use pseudocode. Okay? Pseudocode is a structured design language. Okay? If you follow the rules that we typically ascribe to pseudocode, you cannot design an unstructured program. Okay? But sometimes it's good to get out the old flowcharting symbols and see what the flowchart would look like. So we do the input, we do the conversion, then we do a test. Is a Fahrenheit greater than 90? Yes. Then we print a heat warning. No, we don't do anything. And then we have another test. Is Fahrenheit less than 30? Yes, we print a cold warning. No, we don't do anything. And then the program ends, which I complained about. I thought it should say something like, have a nice day. So either way, we know that we've come to the end of the program. Okay, so what does the second version of this look like? Well, this one has the conditional logic in it. So we're the same. Okay, so we do have something that we do no matter what. I take that back. He does actually print the temperature is Fahrenheit degrees of Fahrenheit. So he does something. And then if it's greater than or equal to 90, he prints a warning. If it's less than or equal to 30, he prints a warning. Okay, well, that's okay. You do have some evidence that it ran even if the two conditionals are not met. And so we run that, and we get the answer that we think we're going to get. So let's talk about the if statement. The Python if statement is used to implement the decision or the selection. So we say if condition, and then we have a colon after the condition, and then we have the body of code. That can either be a single statement or a block of statements. It's indented, one indent, which is typically 4 spaces. Okay? So the semantics of the if should be clear. First, the condition in the heading is evaluated. If the condition is true, the sequence of statements in the body is executed, and then control passes to the next statement in the program. If the condition is false, the statements in the body are skipped, and control passes to the next statement in the program. So here's the example for temperature warnings. If the condition was true, we did, in this case, a single statement, and then we rejoined the main flow of the logic. If the condition was false, then we didn't print any statement at all. So the body of the if either executes or not, it depending upon the condition and whether it is true. In any case, control then passes to the next statement after the if. This is a one-way or simple decision. Okay? Now, I just want to back up and point out that even though this is a one-way or simple decision, the code that we have has two one-way or simple decisions. This is not to be confused with a two-way decision, okay, which we'll see shortly. Okay? So, in fact, if we go back here and find the code, where was the code? Oh, we're ahead of the code. This is the first one. That's a simple or a one-way decision. It's a simple if. Okay? And then immediately after it, another simple if. One-way, simple decision. Okay? Now, don't confuse two simple or one-way decisions that come one immediately after the other with a two-way decision, which is more complex, which we will see in a short time. Okay? Now this is a good time for me to segue off to the first of the programs that I have that's part of the supplemental project, and it's called Decisions 01 Simple. And it's a simple decision using if. Okay, and we put all of our code into the main. So we prompt for a float. In this case, we're not doing a conversion. We don't want to confuse things. We just are getting the temperature in Fahrenheit. Okay, if the temperature is 32 or less, we're going to print Brr, it is freezing today. And then no matter what, we're going to print thanks for playing. All right, so let's test this. See how this works. So, sorry. All right, so let's get a little more room. Okay, so please enter today's temperature in Fahrenheit. And right now I think it's about 45. So I'll say 45. And it says, thanks for playing. Okay? It's going to say that no matter what, because that's not hanging off of an if. That's not controlled by the decision or selection control structure. Okay? Let's run it again, and unfortunately you have to change the size of the type every time. And let's say that the temperature is 30. Okay, well that's less than or equal to 32. Now we should get the warning. And we do. Brr, it is freezing today. And as always, thanks for playing. Okay, so this is my first version of this. It's just a simple decision. Okay, we could put 2 or 3 or 4 of these in a row, okay, and they would be all simple independent decisions. Okay, the question is how many potential paths are in the decision. Okay, in this case we only test for one thing, okay, and we either do it or we don't. All right, let's go back and take a peek at the slides. So, what do these conditions look like? Okay, I think they do a really nice job on this in the textbook and here on the slides as well. We have an expression, which again, of course, can be it can be a variable name. It can be a literal. It can be a formula that's a combination of variable names and literals and function calls. It's some expression. Relational operator, some other expression. So we're typically comparing two expressions. Okay, and we want to know how they relate to each other. Rel-op is short for relational operator. Well, let's see examples. It's easier when you see examples. So here are the relational operators. Now, on the left, we have how they're expressed in Python. In the middle column, we have how they might be expressed in a mathematics textbook. And on the right, we have the meaning. So the less than sign is just the less than sign. Less than or equal, we don't have that symbol on our keyboard, so we type two symbols, less, equal. Equal, oddly enough, we use equal, equal. Why do we do that? Well, because you remember we use the single equal sign for assignment. So the test for equal is an equal, equal test. Let me tell you, there's a lot of program bugs that come from accidentally using the equal sign instead of the equal, equal when you're trying to do a comparison to create a condition. Okay? The next one, greater than equal. Again, two symbols, greater, equal. Greater than, just the greater than sign. Not equal. Well, we don't have a crossed out equal sign, so we use the exclamation point, which is also called the bang symbol. I think because before we got to movies with sound, I think when they shot a gun, they would show an exclamation point. I think that's where bang comes from. In any case, it's bang equal, not equal. Okay, so the exclamation point or the bang symbol means not. Okay, so you can't use these mathematical symbols because we don't have a lot of them on our keyboard. Instead, except for less than and greater than, we make them all up with two symbols in a row. Okay, pretty easy. So there's a warning here on slide number 19 about the need to use equal equal in forming a condition. Use equal equal as the relational operator and not equal, which is the assignment operator. Conditions may compare either numbers or strings. When comparing strings, the ordering is lexographic. That means typical alphabetical ordering that you would see in a dictionary or a phone book. Okay? But they're based on the underlying Unicode and the way characters compare to each other in Unicode, which is slightly different than the way that we would do them. If somebody gave you a list of words, okay, and they all began with lowercase, well, it'd be easy to put them into order, okay? If some of them began with uppercase and some of them began with lowercase, well, you'd have to decide if the uppercase came before the lowercase. Interestingly enough, in Unicode, all of the uppercases come before all of the lowercases. So when we sort into this lexicographic or alphabetical order in Unicode, B comes before A. Even though A is lesser in the alphabetics, all of the uppercases come before all of the lower cases. Okay? Now, can we make adjustments? Yeah, we could shift them all to the same case before we compared them. That's a typical thing that people do. But this is something you should know about Unicode and how they compare. Typically, you want things in the same case before you try to compare them or sort them into order. Gets around that problem. Conditions are based on Boolean expressions. These are named after the English mathematician George Boole. When a Boolean expression is evaluated, it produces a value of either true, meaning the condition holds, or it produces false, meaning it doesn't hold. Okay? So, if you look at the expressions that we were comparing, we were saying, you know, A equal B, A greater than B. So that's either true or it's false. Okay? So these Boolean expressions, all these comparisons, they all yield the result of true or false, depending upon the rules of comparison. In some computer languages, we represent a true as a 1 and false as a 0. And this is a way that they're represented in the underlying machine language, because you'll remember that machine language is binary anyway, and everything is expressed in terms of 1s and 0s. And so a fact that you can represent in a single bit that's either 1 or 0 is pretty handy. However, in Python, we don't fool around with 1s and 0s. We have special values for Booleans. Okay? And let's just look. There are two literals, true with a capital T and false with a capital F. Okay? Now, this is not a character string that is uppercase true. That's a different value altogether. This is no quotes around it, capital T and then RUE. No quotes around it, capital F and then ALSE. Those are the two Boolean values. Okay? They might look similar to the same words without the capitalization. The same words without the capitalization are not the Boolean literal values. Also, if you put these into quotes, well, they're character strings. They're not the Boolean literal values. Well, let's look at this. So, if we ask the interpreter 3 less than 4, okay, it evaluates this condition and it says it's true. Makes sense. Then we say 3 times 4 less than 3 plus 4. And it says false, because 12 is not less than 7. We say character string hello equal character string hello. We get true. We ask character string hello with the capital H less than hello without the capital H. We get true, because all of the uppercase come before, they're less than, they precede all of the lowercase. That's just the nature of the Unicode encoding scheme. Okay? Notice that these are true and false, no no apostrophes around them, no double quotes around them. They all begin with a capital, okay? It's very important that you use exactly these expressions for the Boolean literal values. Okay, so let's look at some interesting thing. This is the thing that I put last in terms of my examples, but I think it makes sense because this is a simple condition that we test. You'll see a lot of Python programs where instead of way down at the bottom, instead of having just an invocation of main, just having main paren, there's an if test. So we say something like, if name equal main, then main. What the heck is going on there? Well, we're going to finally explain that now and show you how that could be useful to you. Okay? So there's several ways of running Python programs. Some modules, by modules we mean .py files. Some modules are designed to be run directly. These are referred to as programs or scripts. So far, that's what we've been running. Others are made to be important and used by other programs. These are referred to as libraries. Now, we haven't done that yet, but I'm going to show you how to do that with my example code in a minute. Some, we want to create a hybrid that can be used as both a standalone program and as a library. Now, I personally think that's probably a bad idea, okay? I think that's probably short-sighted design thinking. So the example I'm going to give you is not going to be a have your cake and eat it too kind of example, okay? I'll show you why you might want to use this conditional code that we're going to learn about, but we're not going to be doing anything as wild as that. Okay. So when we want to start a program, once it's loaded, we include the line main. Okay, not hanging off of an if, just plain old main. It's at the bottom of the code. Since Python evaluates the lines of code during the import process, our current programs also run when they are imported into the interactive Python session or into another Python program. Well, we haven't tried to import one into our Python program before, but we'll take their word for it, right? We have seen it work like that, and when we import them into the Python session, if in fact you followed along with some of the example code that was in the book. Generally, when we import a module, we don't want it to execute, okay? Generally, we import libraries, okay? And libraries are full of classes and functions that we want to use in our code, okay? Without having to code them directly. So, in a program that can either be run standalone or loaded as a library, the call to main at the bottom should be made conditional. Okay, you just say if a certain condition, run the main, and I'll show you a reasonable use of that in a minute. Okay. So whenever a module is imported, Python creates a special variable in the module called name, a Dundername, double underscore name. So a Dundername is the name of the imported module. So if we import math and then we say what's in the variable math dot Dundername, it'll say math. Okay, That's how we know we imported the module math. On the other hand, when we run the code directly and it's not imported, the value of the Dundername is Dundername. So if in fact we load up a program and we ask what's in Dundername, we'll get Dundername. To recap, if a module is imported, the code in the module will see a variable called Dundername, whose value is the name of the module. When a file is run directly, the code will see the value Dundername. We can change the final lines of our program to check that, and only run it in the case that it has been brought in to run as the main program. So we can check if Dundername equal Dundername. If that's true, then we want to run main. Virtually every Python module ends this way. Okay, my Python modules don't, because this have your cake and eat it too design is, I think, kind of old-fashioned. Okay, but you will see code like this, and you have to know how it's going to behave. So we're going to teach you how to do it right here in Chapter 7. Okay, so where does he go? He goes on to Quadratic Equations. Okay, not going there. So where are we going to go? Well, let's go take a look at this. This idea that we might want to sometimes run a module directly, and then sometimes we might want to import it. Well, typically for me, if I have a module that I'm not going to run directly all the time, it's going to be holding things like utility functions. So I just created a module, okay, and it's called Decisions 55 because it's almost at the end of my list of examples. My utility functions, okay, and what's my explanation of it is a module containing commonly used functions, okay, and there are two functions. One is miles to kilometers, and the other one is meters to inches. And my thought is that maybe we would create like a whole set of these, okay, and anytime we needed to do a handy-dandy conversion calculation, well, we would import this module, and then we could use the functions that were in the module. Okay, well, that's fine in terms of you want to import it. What might you want to, what might you want to do if you ran that code all by itself? Well, for me, I might want to just run a unit test of the code. I might just want to say, okay, I would like to run a test case, all the test cases that this code has to pass in order for me to know that it hasn't been broken. Okay, well, I think I already showed you in the last, I may not have shown you this yet. One of the things that you can do for this is, so how do we test miles to kilometers? Well, we'll know that's going to be working if we call it with 1.0 and we get back the conversion factor, 1.609344. So here's what I do. I have first of all, I have a variable that's a Boolean, and I say that it's true. So I assume that we're going to pass the test, okay? And then I'm going to run each of the tests, Every time I run a test, if it fails, I'm going to turn pass to false. Okay, so here's my first test. I'm going to test miles to kilometers. If that works the right way, well, I'm going to leave it true. Then I'm going to test meters to inches. If that works as advertised, then I'm going to leave the answer as true. In the end, I say if passed, print all tests for my utility functions have passed. This has another name now. So this is something that didn't get changed. So this is called Decisions 55, my utility functions. My utility functions. Else, this is a two-way decision. Okay, the reason I put this at the end was I guess I had a two-way decision in it, and well, he put this in the beginning, so I guess he wasn't going to show you this two-way decision code. But this is a typical thing that you might do after a group of unit tests. You would say if passed. So for these Boolean variables, okay, you can test if they're equal to true by just asking the name. You can say if passed. That's the same as saying if passed equal true. Okay. So we say if passed, print all tests for the program have passed. Else, what do we know? Well, excuse me, we know that some tests for the program have failed. Why not all? Well, it could have been that only one of them failed. Okay? Now, is this a really rigorous unit testing framework? No, it's not. Okay? And maybe we would have a more rigorous unit testing framework. Okay, but one use of this conditional execution down at the bottom is if we just run Decisions 55 my utility functions, well, then it's going to load and it's going to pass the test if a Dundername equal Dundername, and we're going to call main will run the unit test. If, on the other hand, we are importing Decisions 55 my utility functions into another program just to use as a library, this is not going to pass, because is name going to be equal to Dundername? No, it's going to be equal to Decisions 55 my utility functions. So it's not going to run main. Okay, so let's take a look at what happens when you have this and you run it by itself. So I'm just going to right click and run it, and here it is. It says all tests for Decisions 55 my utility functions have passed. Pretty cool, right? Now, what if we were to use it in another context? What if we really use this as a library? Oh, okay. Let's look at Decisions 60. Use my utility functions. Here it is. Okay. So here's the name up top. A program that uses, I guess this should say Decisions 55. Decisions 55 my utility functions module. Okay. So we say this. We say from Decisions 55 my utility functions, no .py. Okay, so the name of the module, the .py is what makes it a module. Okay, so from module name import function name, meters to inches. Okay, so and then we can use just testing the import, and then now we can actually use meters to inches in here. So why do I have just testing the import? Well, I want to show you that we don't, if we can import this and we can not use it. So let's toggle that into a comment. You'll see that the import's not really used here. But it's going to get imported anyway. So let's run this program. So we run it. Okay, and it says just testing import. You'll notice that it didn't run the main in Decisions 55 My Utility Functions. We don't have any output from it. You don't have that unit testing passed, right? Why? Well, because we're using it in a different context now. So when that gets imported, okay, it still goes down and it looks at the it goes down and it runs the test, but that test fails, so it never runs main. Okay? Okay, so let's actually use the code that was in there. Let's untoggle that. And I think I have an extra blank line here, so I'll get rid of that. Okay. And now I say 20 meters is equal to meters to inches 20. I could say 20.0 here. That'd be nice. That's a float. If I pass it in int, it's going to convert it anyway. Inches. All right, let's look. Let's give this guy a run. So it says just testing import. 20 meters is equal to 787.4 inches. Great. Okay. So if you are creating some kind of module to hold utility functions, and later perhaps utility classes, those kinds of things that you want to import and use, you can have a main in there. Okay. In this case, I decided that it would hold test code, and we would only run the test if we ran the module all by itself. If we, in fact, use it in the more normal way, where we just import it, the test code does not run. Okay? So that's a typical conditional logic. Okay? Now, for me, if I'm writing a typical program or script like this one here, I don't put that conditional stuff over top of it. I wanted this to be clear that this is the way I intend to run this. I don't intend to import this into something else. This is just a mainline program. Okay? So the only time that I personally put this conditional execution for main is in some case where I've got some conditional code that I want to execute. And again, the best case of that in terms of what we know now is perhaps for unit testing. All right? Okay, so that's that one. So where do we go from here? Well, let's take a look back at the slides and see where the author goes with the slides. He goes to two-way decisions, but he goes crazy. He goes into quadratic equations. Okay, well, you know, we can get into two-way decisions and talk about the weather. Okay, we don't have to talk about quadratic equations. Let's be a little easier on ourselves, and let's talk about the weather. So I'm going to close these modules, which we're already done with, and I'm going to open up Decisions 05 two-way decision. Okay, So let's look at this. Well, what do we see? Well, we do the same thing we did in the simple one. Okay, we prompt the user to give us today's temperature in Fahrenheit. Now, I just want to point out something here. You know, the Zelle textbook, he puts his character strings into double quotes, right? Now, I've been trying to model the alternative for you, so I went through and I changed these I had in double quotes. I changed them to use apostrophes. You just have to note that when you have an apostrophe inside of a string that you've enclosed with apostrophes, you have to put 2 apostrophes to have it count as an apostrophe. Okay, this is, I think you would call this an escaped apostrophe. Okay, so it doesn't end the character string, it's simply these 2 collectively say, oh, I really mean an apostrophe here, I don't mean to end this string. Okay? So then we say if temp is less than or equal to 32, print brr, it's freezing today. Else, print well, at least it is above freezing today. Okay? And in any case, okay, it print thanks for playing. All right, so make that code a little bigger. All right, so let's execute that. We're going to run, and we say, what's the temperature in Fahrenheit? So again, it's maybe 45 today. And it says, well, at least it is above freezing today. Thanks for playing. All right, that's good. Let's run another test. Let's say that overnight it drops down to 30. 30. Brr, it is freezing today. Thanks for playing. This is your typical two-way decision. Okay? There's an if and an else. Something that is pretty obvious, I think, to us, because we've been working with code blocks all along, right? Because we learned how to create a loop, and the body of a loop is a code block. Now, this is the body of an if, or the body of an else is a code block. Now, the trivial case is when it's just a single statement. Okay, what if you have more than one? Well, you would say something like print next statement, right? You'd have something like that. And so you could have 2 statements. You could have 3, 4, 5, 6, 7, 8, 9, 10, right? Same deal. It's a sequence. The trivial case of a sequence is one statement. A more typical case is several statements. Okay. A challenging case is where one of the statements in the block is a call to a function. Okay. Then as we're going through the sequence, we're going to go out, do the function business, and then come back and then go to the next statement. We saw that back in chapter 6. Okay. So you can have a single statement in the code block or just one. Okay. The same here. Okay. Now, there's actually another statement that you can use. There are times. This is odd. This is kind of an indirect way of coding. What if you didn't want to do anything? Okay, what if you wanted no statements. Well, I think you would say, well, then you need a simpler control structure. But it's actually possible to take one of these, say this first one, and let's cut that. You can actually say pass. What does pass mean? Pass is a non-operation. It's a no-op. It's a do nothing. So we say here, if temp is less than or equal to 32, don't do anything else. Print, well, it's above freezing today. Now, that doesn't look like good code. It's better code to tell a user one way or the other, give them some useful output. Okay, so I just wanted to point out you can have a code block that's got 1,000 statements in it, although that's too big. Could it have 10? Yeah, that's not a bad size. Could it have 3? Yep. Could it have 1? Yep. Could it have none? Well, not typical, but here's how you would express it if you had it with the word pass. Okay, so let's undo that because that's not what we want. Okay, and also, you know, I've been separating code for you guys in the examples that I've been doing. I've been putting blank lines around things for drama. So before the if, I could have a blank line. And after the if, I could have a blank line. Okay? That makes it a little bit clear that we don't just go on and do the print thanks for playing as part of the else. Okay? Sometimes when we've got beginning programmers and they don't have these blank lines in here, it's hard for them to see the difference between this, which is going to print thanks for playing if the first test is true or if it's false, with this, if we indent that, then it's only going to say thanks for playing if it's false. Okay, which is definitely not what we want, right? So if we run this, if we say that it's 10 degrees out, it's just going to say, brr, it is freezing today. It never says thanks for playing because that got swallowed up by the else block. Okay, if we run it again and we say it's 90, there's our thanks for playing. But our thanks for playing really belongs out a level. Okay? So if there's nothing wrong with the code that we have here, could you skip a blank line before this final print for drama and to emphasize that it's not part of the loop? Sure, you could, or not. One's not right or wrong, but if it helps you to do this, then certainly do it. Okay? But the code I've got here is going to work just fine. All right, so that's the two-way decision. Okay? You do the else block only if the test was false. You do the if block only if the test was true. All right? Pretty cool stuff. All right. What's next? Multi-way. All right. Do we actually do the multi-way? Let's go look. 2 ways. It goes all through the 2-way stuff. 2 ways, multi-ways. Then he goes right into multi-way. And he's still fooling with quadratic equations, which good for him, but I think it's too mathy for your average new programmer. If it's not, good luck on your math. I'm proud of you. Okay, so I'm going to close this one and open up Decisions 10, multi-way. Okay, so what if we've got more than two alternatives? Okay, well, it turns out that in Python there is a construct for three or more alternatives. Okay, and it's called the else if, which uses an operator called elif, which is just short for else if. Okay, do you have to call it elif, or could you call it else if? I've heard people call it both. Okay, so you can certainly use both for me. Let me make this a little bit bigger, and I'll be happy to understand either one. Okay, so what are we doing? Well, there are three situations. Okay, if it's less than or equal to 0, then I want to print watch out. It's Chicago cold today. I say that because I live in the Chicago area. elif, if it's less than or equal to 32, say brr, it is freezing today. Else, print well, at least it is above freezing today. And then in any case, I always want to print thanks for playing. Okay? So, couple of interesting things here. As soon as you get a sequence like this, as soon as you have this multi-way comparison, you have to start thinking about the order in which you test for stuff. Okay? If something's only going to be true or not, if we go back to the two-way, okay, if you go back to the two-way, you don't have to do them in any particular order. You could have reversed the test, in which case you would put the code blocks in the opposite place, right? And it'd be just as easy to read. It would work just as well. We probably have this kind of sense that we want to check for lower things first and then have the code for higher things later. But, you know, there's no reason, there's nothing that really forces us to do that. When we get on to multi-way, we need a scheme. We either have to be going from the lowest of the values to the highest, or from the highest to the lowest. I tend to go from the lowest to the highest. Okay, I think that's the best practice. So the first test I do is my lowest test. I say if the temp is less than or equal to 0. The next thing I test for is the next higher one. I say else if the temp is less than or equal to 32. Okay? And then at the end, I don't have to have a final else. Okay? This is optional. But it's good practice to always have an else. Okay? Because if you drop off the bottom of one of these, I think you want to know. Okay? You don't want to accidentally fall through the 0 test and the 32 test and not have any particular behavior to tell you that you've gotten there. So for me, even though I could have said if temp blah blah, elif temp blah, and not have this, coding the else is the best practice. So I'd like to see you do that. Okay? So first we tested for 0, then we tested for 32, and then we had some behavior that was appropriate for above 32. If we were testing, and I'm gonna show you one in a minute that goes even farther, which is to say we test for more than 2 things. Okay? Well, just remember that you need to test for them in order. Okay? Because these tests only work if they're done in order. Okay? If you were to shuffle them up and test for 32 before you test for 0, you wouldn't get the right behavior for the right conditions. Okay, so did we do this one? I forget whether we did this one or not. We'll do this one again just because it's fun. So this is the multi-way, and the first one we're going to say it's minus 200. It's Chicago cold today. And we're going to say it's 12. It's freezing today. And then the last one we're going to say it's 75. 75. Say, well, at least it's above freezing today. Thanks for playing. Okay, so this temperature stuff, talking about the weather, is a great way to learn the different decision constructs. Okay, so we have the simple, we have the two-way, and the multi-way. What's the simple? Well, let's look. The simple has just the if. Okay, what's the two-way? Well, the two-way has the if and the else. Okay, what's the multi-way? Well, it has the if, the elif, and typically it's going to have a final else. Okay, now what if it's more than three-way? Could it be four-way or five-way or six-way? Sure, it could be. That's why I created Decisions 15 multi-way extended. Let's look at that. So here we have a bunch of them. Let's see. So we test for 50, that's 1, 20, negative 50 is 1, negative 20 is 2, 0, 3, 32 is 4, 40, 5, 70, 6, 80, 7. So we categorize, we've got 7 categories that it can fit into. Okay, and we want to pick the right one. Else, we're going to pick one more. That becomes an 8th category. That's it is equal to or hotter than 80. So we've really got 1, 2, 3, 4, 5, 6, 7, 8 categories. And each one has the behavior associated with it. Okay? Now, I've got to emphasize, these tests only work in this else if kind of construct. They only work if you code them in ascending sequence. I mean, you could have the test go the other way and code them in descending sequence. I don't think there's really a good case for that. So this is what you typically see. All right? Now, if we mix these things up, if we took the test for 80 and we stuck it down the bottom, we'd start to get some wrong answers. Okay? You can experiment with it a bit and see what I mean, but believe me, you're going to get the wrong answers. Okay, well, let's just do some testing on this. I'm not going to test every one. I'll leave some for you to test on your own. Okay, so let's run this. Okay, so let's see. Let's try negative 100. What do we got? Oh, that's wrong. I'm in the wrong window. Sorry about that. You have to click down here. Negative 100. Careful, it is Arctic cold today. Okay. That's what happens if it's not minus 50 or less. Okay. What happens if it's minus 20 or less? Okay, between 20 and 50. So let's run it again. Okay. And let's say minus 25. And it says, watch out, it is Minnesota cold today. Now, I'm not from Minnesota, but it gets colder there than Chicago, as those of you from Minnesota well know. Okay. And there's one more that I want to show you is what if it's between 40 and 70? So what if it's 65? Well, if it's 65, we say we can expect to see undergraduates wearing sandals today. That also happens at 40, which just happens to be true at American universities in the spring. Okay, good. So you can do the rest of the testing with this, but this is a typical construct. Once you get to 3 or more, you want to use this elif construct. Okay, and it's really important to put them in ascending order. You could put them into descending order, like I say, but I don't think that's worth doing. Always, my rule for me, always put them into ascending order. Okay, I think that's a good practice. All right. So that is that's where we're going to stop for part 1. Okay. So I'm going to finish up on part 1 right here. I'm going to take a break, and I'll be back for part 2 in a couple of minutes. See you then.